Hi, and welcome to this lecture on laminates and toughness. Let's start with talking about laminates, a combination of fibers and a matrix material to hold the fibers into place. As you know, some materials are anisotropic, meaning the material has different properties in different directions. So how can we use that in creating specific aircraft or spacecraft materials? Let us have a look at this piece of material. This material is made out of carbon fiber and has predominantly fibers in the 0-degree direction. It is already pre-impregnated with epoxy, so it's a bit sticky. On its own, it's very flexible. So in order for it to also maintain its required shape, it is embedded in epoxy resin and baked in the autoclave. This results in a piece of solid material such as this. The resin is often referred to as the matrix. This combination of a matrix and a sheet of woven fibers to form a material is shown here schematically and is also known as a ply. With fibers predominantly in the 0-degree direction, it is now also easy to understand that the modulus of elasticity in longitudinal direction, EC, is much larger than the modulus of elasticity in transverse direction, E'(C). If we look at the stress-strain diagram, we can see three lines. The lower one is the curve of the matrix material, which is very ductile but not very strong. The upper curve shows the behavior of the fibers on their own. As you can see, the fibers are very brittle. The middle curve is what you get if you combine the two into a ply. You can see that its characteristics are a function of the two. The volume fiber fraction of the 0-degree fibers determines the ply stiffness. The higher this fraction, the closer to the fiber behavior the curve will go, and vice versa. Tinkering with the fiber volume fraction and stacking plies under different orientation on top of each other, as is shown here, allows us to tailor material to the properties we are looking for. This combination of ply layers is called a laminate and is also referred to as a composite material. Another important material property is toughness. Basically, it tells you how hard it is to break a material. So, we can look at toughness as the resistance against breaking. This is often represented by the area under the stress-strain curve and has the unit of joule per cubic meter or the energy per unit volume. If we look at the stress-strain diagram for three types of carbon steel, we can observe that high strength does not necessarily equate to high toughness. Toughness is indeed a separate material property to consider when selecting a material for your design. There are different types of toughness depending on how a material breaks. I will discuss two types here. First, impact toughness, which is measured by carrying out a Charpy impact test. This involves having a swing hammer device hitting a notched specimen and measuring the energy needed to break the specimen. Secondly, fracture toughness, which is determined by measuring the energy needed to fail a specimen containing a crack, as you can see in the picture.